All right, and a big hello to everyone who is rolling in. This is Cheg's live Trig office hour. We are excited to dive into Trig with you. I'm at Wallace STEM. You probably know me from my channel at Wallace STEM, where I do memes about all sorts of hilarious trends, but they're all about math. So come for the memes and stay for the math is my tagline. For those of you that have joined one of our live events before, welcome back. We're excited to have you. Today, we're talking all about trigonometry, helping you in those pre-calculus classes. Every week, I'm going to be here working on trig problems with you on Wednesdays at 5 o'clock Pacific time, 8 o'clock Eastern time. So make sure you mark your calendars and you join us for this virtual office hour. I'm here to help you. So put your questions into the chat and I'm going to try and answer them. I'm going to check this out really quick. It looks like we're already getting some people giving us a few comments, but as those comments come in, let me start off with saying why I really love trig. What I love about trig is there's a lot less to actually memorize, because if you really focus on understanding how all of the concepts work together, there's a lot less to memorize. For example, the unit circle is the foundation and heart and soul of everything we do in trig, right? Well, if I put a point on the circle, that point has a length and a height. That length and height is really what defines the coordinates of that point. The length, we call that the cosine. The height, we call that the sine. And the hypotenuse, if this is a unit circle, the hypotenuse has to be 1. Well, that's a right triangle. We know how right triangles work using the Pythagorean theorem. The Pythagorean theorem says a squared plus b squared equals c squared. So if I take my sine squared and add to it my cosine squared, that's going to equal my hypotenuse squared, which is 1. And this gives us the most important identity that we have probably in all of trigonometry, that sine squared plus cosine squared is 1. It's all based on the unit circle. Well, students often have to complain that they have to memorize like 3 different Pythagorean identities for their proofs, those proofs, the heart of everything we do in trigonometry, right? What's really neat is if you know this one, you don't have to memorize the other 2, because if I wanted to divide each one of these terms by sine squared all the way across, I end up with sine squared over sine squared. Well, that's just 1. Cosine squared over sine squared, we know that relationship. That's a cotangent squared. And 1 over sine squared, we also know that relationship. We call that the cosecant squared, because cosecant is the reciprocal of sine, and that's going to give us our second Pythagorean identity. So I don't have to memorize it. I know I can get it from the other one by just dividing each term by sine squared. Similarly, we can go back and divide each term by cosine squared. If I go through and divide each term by cosine squared, we'll get another Pythagorean identity. Let's write this one in Cheg orange. Sine squared divided by cosine squared is the tangent squared. Cosine squared divided by cosine squared is 1, and 1 over cosine, the reciprocal of cosine, is secant. And so in this way, I don't have to actually memorize the other formulas. I just have to know sine squared plus cosine squared is 1, and I can get the other formulas. Generally with trig, if you know how the things are connected, there's a lot less to keep track of. So tell me what you're doing in your trigonometry classes. What should we practice doing? Do we need to do some proofs? Do we need to do some solving? Are you doing some graphing? What are some topics you're looking at? Stick them in the chat, because this is your Trig office hour. I'm excited to see everybody logging in. Let's do one of those graphing problems. Actually, let's make it an application of a graphing problem. These often show up on test. For example, let's say I have a Ferris wheel. There's my little Ferris wheel. See, there's my little people. They hang. Now, the Ferris wheel doesn't come down and touch the ground. There's a little bit of a platform that the Ferris wheel is built up on, right? So there's the platform that the Ferris wheel is built on. Now, the Ferris wheel needs to have some diameter. So let's give the Ferris wheel a diameter of, let's call it 20 meters. And this platform here lifts it up off the ground even higher. Let's say this platform has a height of 2 meters. So you get on this Ferris wheel, you can ride it around, and it's going to go up and down, up and down. Let's say it takes 24 minutes to complete a full revolution. What we're going to do is we are going to create a graph to model how high you are on the Ferris wheel at any moment in time. Then we can use that graph to answer questions like, how often are you above 17 feet? Well, let's break this down with this graph. The first thing we need on any graph is we need to know where the midline is of this Ferris wheel. So to get to the middle of the Ferris wheel, how high total am I going to be? Stick it in the chat if you know the answer. How high am I going to be for the middle of that Ferris wheel when I reach halfway up? If you put 22 meters, that's not right. I did it wrong. 20 meters is the whole diameter. 10 meters is the radius. So we got a radius of 10 meters and an extra 2 meters. We're up here at a midline of 12 meters. And then to the top and bottom, it's going to go halfway up the circle, or a radius of the circle. That's going to be 10 meters up. So 10 meters up. The top is 22 meters. So that's the top of my graph. The bottom of my graph, 10 meters down, is 2 meters. So when I get on my graph, where am I getting on my graph? I saw some great answers, by the way. I forgot to call you out. I should have called you out. Sir Lewis, you got the right answer. David Torres, also 12. You're both doing better than me because I said 22. I forgot we had to take a radius. Good job on catching that. So when we get on the Ferris wheel, where do you get on a Ferris wheel? Do you get on at the bottom, the middle, or the top of a Ferris wheel? Well, makes sense. We can't fly. You go up on the platform and you get on at the bottom of the Ferris wheel. So before any time begins, I get on at the bottom of the Ferris wheel. Then the Ferris wheel is going to take me up to the top and back down. And we know the total time that's going to pass is 24 minutes for me to make a full revolution. That's not a very beautiful curve, but we get an idea of what the curve is doing. Let's see if we can pull off of this curve the important stuff that we need to make an equation. First thing I see is the equation is starting here at the bottom of the graph. Which trig ratio starts at the bottom? Is it sine, negative sine, cosine, or negative cosine? Which one is it going to be? Sine, cosine, negative sine. It's really easy to get those mixed up. What I like to remember is sine starts from the middle, cosine starts from the extreme. And since we're starting at the bottom, this one's going to be a negative cosine. So we've got negative cosine. We need something that goes in front of the cosine. The number in front of the cosine tells us the magnitude or the size that this thing is going to go from the midline. So from the midline, we're going to go up 10 and down 10. That magnitude, we call it the amplitude, is the number that's going to go in front of the cosine. So we have negative 10 cosines. Inside here, we're going to have a period shift. How long it takes to go the entire distance is 24. But do you remember we don't actually put the number 24 into the formula. We have to do something to the 24 first before it goes into the formula. Go ahead and stick in the chat. What do you think it could be that we're supposed to do with the 24? We don't put 24 in. What do we do? I got Sir Lewis is hot on answering questions, so maybe you can get the answer in there before Sir Lewis. See if you can beat Sir Lewis. Remember, with a unit circle, a total distance around is 2 pi, or 360 degrees, but we're going to go in radians. So we need to take that 2 pi, and we're going to divide by the total period length. So 2 pi divided by 24 is our time. The next thing we have to add is we have to add the phase shift. That center line has shifted up 12. And so we end up with this function. We could call it f of t. This function tells us how high we are on the graph or on the Ferris wheel at any point in time. So let's say we want to know when we're at 17 feet. So I'm right here, 17, not feet, sorry, meters, 17 meters. I want to know when I hit 17 meters. We're going to make this equal to 17, and that gives us a trigonometric equation that we know how to solve. Let's go ahead and solve this. This problem's taking longer than I'd expected, but that's okay. This is a good problem. They're great test problems. The AP Calculus, Pre-Calculus test loves these. We want to get this cosine alone. So to do that, we're going to subtract 12 off of both sides. When I subtract 12 from both sides, I get 5 equals negative 10. Cosine of, I'm going to go ahead and reduce this to pi over 12 times t. Then to get rid of this negative 10, we're going to divide both sides by 5. No, not by 5. By negative 10, sorry. We want to get the cosine alone. Dividing by negative 10, we have 5 divided by negative 10 is negative 1/2 is equal to the cosine of pi over 12 t's. Well, let's think about our unit circle. We want cosine, the x-coordinate, we want cosine to be negative 1/2. The x-coordinate is negative 1/2 right here at the top and bottom. What is that? Well, the first one up here is 2 pi over 3. This one down here is 4 pi over 3. We hit 2 pi over 3 first. That's when we're going to first hit that point of 17 meters. So I'm going to use this first one, 2 pi over 3, and set that equal to the pi over 12t to get the equation that we're going to solve. So pi over 12t is equal to 2 pi over 3. In order to solve for how much time it takes me to get up here to 17 meters, we're going to multiply by the reciprocal, which is 12 over pi, which is really nice because then the pi's reduce out and 12 over 3 reduces to 4. So t, the amount of time it takes me to get up to 17 meters is 2 times 4, or 8 minutes. So after 8 minutes, I have come up and risen to this height of 17 meters. So that is my favorite application problem of all of trigonometry, I think. The Ferris wheel problem, maybe it's because I love Ferris wheels, but what questions do you have about trigonometry? What are you working on in your trig classes? I see a comment from Jenny on TikTok who wants to go over how to verify using trig identities. So let's do that next. And while we're looking at Jenny's trig identities, if you have a question you want us to answer and go over from your trigonometry class, stick it in the comments and we'll do our best to answer it along the way. And by the way, I am so excited to have you joining this live, but I want to make sure more people know about this and can join us as well. So make sure you're hitting the like button, but also the share button. Share this live with others by just hitting that share button, and I'll really appreciate it. Then more people can join us and we can take a look at those. So let's do some identities. Let's find a fun identity here. Trig identities are like the heart of trigonometry. Let's do this one. Let's say secant squared of theta over 2 minus secant squared of theta. That equals the secant of 2 theta. All right. There are lots of strategies that we can use to go about solving trig identities. The most common one that I use, I kind of got too close to the QR code with that problem. Sorry about that. Hopefully you can still see it. By the way, you can scan that QR code and stay updated on all of the lives that Chegg is doing to help you with all of your classes right now. So check that QR code out. But for now, we're going to solve this proof. With a proof, we only can work on one side. So I can either work on secant and make it look like this fraction, or I can work on this fraction and make it look like this secant. I always like to start with the more complicated side. That's usually the easier one to simplify. So let's start on this left side. And if I don't see anything I can do right off the bat, what I'm going to do is I'm going to change all of the secants into sines and cosines. Secant specifically is the reciprocal of cosine. So we have 1 over cosine squared of theta over 2 minus 1 over cosine squared of theta. That will often create a situation where we've got little fractions inside of a larger fraction. Whenever I have little fractions inside of a larger fraction, we can get rid of those little fractions by multiplying by that denominator. So we've got cosine squared, top and bottom, we're going to multiply, and then it's going to distribute onto both terms. So we're also going to multiply the cosine squared over here, which is nice because these cosine squares reduce and these cosine squares reduce. And so I just end up with a 1 on top and 2 cosine squared minus 1 on the bottom. All right, now we're looking for something else that looks familiar. 2 cosine squared minus 1 should look familiar as an important identity. Do you remember what that simplifies to? See if you can stick it in the chat. What does 2 cosine squared minus 1 simplify to? Well, while you're putting that in the chat, I saw a question about my previous question. Shouldn't we list all the times the height is 17? You're correct. As you go around the Ferris wheel, you hit the 17 lots and lots of times. But I didn't write it down, but the way I worded the question when I wrote it down is we wanted to find the first time we hit the height of 17. But you're right, we can go through and find all of those. All right. Did you come up with 2 cosine squared minus 1, what that equals? That's one of our trig identities. It is the double identity of cosine of 2 theta. So if this is 1 over cosine of 2 theta, it's the reciprocal of a cosine. We have a trig ratio that's the reciprocal of cosine. The reciprocal of cosine is the secant, and we keep that 2 theta in there. So secant of 2 theta is exactly what we're looking for. This proof is done. Notice how we did that is we started with the left side, played with it to make it look like the right side. With proofs, we can only work on one side. Great question came in from TikTok. Can we do some trig u sub? Are you talking about like integration with trig u sub, or are you talking about using substitutions to help us with solving trig? Because those are very different topics. So maybe you can clarify that a little bit and we can come back to it. I know on Tuesdays we do a calculus study session. So if you're looking for the calculus question, Tuesdays at 5:15, I think, is when we do our lives on calculus. So check those out. Closely related to solving using trig identities or proving using trig identities, we can also do solving equations using some trig identities. And it's kind of related to those proofs that we were taking a look at. So let's try this problem. Let's do, oh, there's so many good ones. Let's do 2 cosine squared. Actually, let's do sine squared. 2 sine squared of theta equals 3 times 1 minus cosine of theta. And since we didn't do it last time, let's go ahead and find all solutions this time. Because somebody brought up the question, shouldn't it be every time we pass 17? Yeah, let's do every single time and see what happens. So the first thing we need to do when solving is it's very difficult to have sine and cosine in the same problem. It would be really nice if we did not, and if we just had cosines. What's nice is this sine squared, we can change using that identity from the very beginning of our live stream. Were you watching then? Sine squared is 1 minus the cosine squared of theta. Everything else stays the same. And because we're solving, not proving, because we're solving, we're allowed to work both sides now. Well, when we have a number in front of parentheses, we know what to do with that. We're going to distribute through the parentheses, giving us 2 minus 2 cosine squared theta equals 3 minus 3 cosine theta. And this is kind of what I was thinking you might mean when you mentioned that u substitution. But I think you were talking from another comment. You said the calculus version, the integration version. But where I often see the u's used, you say that 5 times fast, the u's used. All right, is we replace the cosine with u, and then u squared is cosine squared of theta. And that can help us kind of see the substitution that we're working with in order to solve this problem. So now I've got 2 minus 2 cosine squared, that's u squared, equals 3 minus 3 cosine, that's our u. We know how to solve problems that have u squared and u in them. That's just a quadratic. We're going to set this thing equal to 0, hopefully factor it, but if it doesn't factor, we have the quadratic formula to rely on. So let's go ahead and add the 2u squared to both sides. And we've still got the minus 3u. When I subtract 2 from both sides, I'm left with a positive 1. And now it equals 0. And this we can hopefully solve. Let's see how it goes. 2u squared is 2u times u. 1 is 1 times 1. And if they're both negative, that'll give me the 3u in the middle. So let's come back up here. My pink is dying. Can you still see the pink? Let me replace the pink with red. Need to get new Expo pens. All right, so we're going to take the 2u minus 1, set that equal to 0. The u minus 1, set that equal to 0. And then I can solve both of these to get solutions. If I add 1 and divide by 2, u is equal to 1/2. If I add 1 here, u is equal to 1. But remember, we weren't actually talking about just u's. We were talking about, I don't like that though. U, we said, was cosine. We want to know when the cosine of theta is 1/2, and we want to know when the cosine of theta is 1. Well, to do that, we just have to think about our unit circle. Cosine is the x-coordinate. So the x-coordinate is a positive 1/2. That happens both here and down here. What is that in radians? That's pi over 3 and 5 pi over 3, I think. Yep. And the cosine is 1, the x-coordinate is 1, way out here, and that happens at 0. But that's just the first revolution around the circle. Remember, somebody was asking earlier, what about every time we pass that? So let's take a look at how that's going to work. We start with this pi over 3. And every time around the circle, we're going to get a new solution. So we have to add 2 pi times n, because 2 pi is a full circle. So every n, we get a full circle. So when n is 1, we go around once. When n is 2, we go around twice. When n is 3, we go around 3 times. That gives us all the solutions for pi over 3. 5 pi over 3. Also, we get another solution every circle. So we'll add 2 pi times n. And 0, don't have to write the 0, but let's write the plus 2 pi times n, or every time we circle the entire circle. All of these will give us a solution to this original equation. Excellent. I am looking at the questions coming in. We're getting some great questions. Find the angle formed between 2 lines. Given 2 points in Cartesian coordinates, is it possible to determine the angle formed by the lines between them? If you have the lengths, you can. I think that would work. Let's take a look at that question. I want to play with that question from TikTok, from Joe. Can we figure out the angle between some lines? By the way, this is your Trig Office Hour brought to you by Chegg. Hopefully you're logging in from all over. In fact, if you don't know what to ask me in the chat, just tell me where you're coming from in the chat. I would love to see where you're all logging in from on whatever platform you're logging in on. The question was about Cartesian coordinates, and we want to determine the angle formed between them. Let's see. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Let's say we've got a point here at 1, 1. And another point here at 1, 2, 3, 4, 1, 2, 3, 4, 5. So that's going to give us a line that connects those 2 points. Then we're going to have another point. Let's go. I don't want to make a right angle, but I want to make it come out nicely. Well, it doesn't have to come out nice. We'll just use a calculator. How about that? Let's put another point over here at 1, 2, 3, 4, 5. I'll do it a different color. 1, 2, 3, 4, 5, comma 2. And we're going to try and find the angle between them using trigonometry. And there's a couple ways to get about it. One way is first, if we know both of these lines, and this distance here, this third side, if we know all 3 sides of a triangle, we can find the angle using the law of cosines. So let's find the lengths. The length, we find the length by the Pythagorean theorem. So for this green one, it goes up 1, 2, 3, 4. It goes over 1, 2, 3. We could also, if we wanted to, get that by subtracting 5 minus 1 is 4, and 4 minus 1 is 3. This side, then, we can find with the Pythagorean theorem, 3 squared plus 4 squared is the hypotenuse squared, 9 plus 16, or 25. So we end up with 5 is equal to that hypotenuse side. Good. All right. Now we need the red line. This one's not going to come out as nice, but the same pattern can apply. Its length is 1, 2, 3, 4, but its height is 1. So the Pythagorean theorem says a squared plus b squared equals c squared. So we have 1 plus 16 is c squared, or 17 equals c squared. So this length here is the square root of 17. Then we have to go through and find this side. Well, this side goes up a distance of 1, 2, and over 1. So again, a squared plus b squared, 1 squared plus 2 squared equals c squared, 1 plus 2, so 3 is equal to c squared. C is the square root of 3. We got a lot of stuff happening in this picture. I want to try and clean it up a little bit so that we can focus on it. But the question that was specifically asked was about using the coordinates to find the angle between. Now that I found all 3 sides, I'm going to redraw this triangle. Nice and big for us. Not to scale. We found out this side was 5, this side was the square root of 17, and this side was the square root of 3. And we wanted to know what was the angle formed between those 2 lines. This is where we use the law of cosines. Wouldn't 2 squared be 4? Did I do that wrong? I did, didn't I? Thank you for catching that. CR243. 1 squared plus 2 squared is c squared. So it's 1 plus 4 equals c squared. So c squared equals 5. C is the square root of 5. Thank you for catching that. It should be the square root of 5, not the square root of 3. Okay. All right, So the idea of the law of cosines is it's a lot like the Pythagorean theorem. The law of cosines says a squared plus b squared equals c squared. The difference with the Pythagorean theorem is the Pythagorean theorem requires us to have a right angle. We do not have a right angle in here. At least I don't think we do. So instead, we have to have this correction factor where it's actually a correction term. We subtract 2 ABs times the cosine of the angle between A and B. So this is the angle between A and B, which means 5 and the square root of 17 are my A and B. C is the other angle that doesn't, or the other side that doesn't touch the angle. So if I plug these values into my formula, we end up with A is 5 squared plus B, which is the square root of 17 squared, minus 2 times A, which is 5, times B, which is the square root of 17, times the cosine of C, that's the angle we're looking for. That's the angle we're looking for, is equal to C squared, which is the square root of 5 squared. Well, let's take a look at solving this. I'm going to use a calculator. We've got 5 squared plus the square root of 17 squared. We can simplify this part, but we can't simplify this part yet because it's with the cosine. 5 squared plus 17 squared gives me 42 minus 2 times 5 times the square root of 17. That's going to give me 41.23 cosines of C equals the square root of 5 squared is just 5. Okay, let's keep solving. We're going to solve by subtracting the 42 from both sides. Ultimately, we're trying to solve for that cosine. So we have negative 41.23 equals 5 minus 42, that's, cosine of C. 5 minus 42, that's going to be negative 37. And then we get the cosine alone by dividing both sides by negative 41.23. That's going to give us the cosine of C is equal to, I can't do that one in my head. So back to the calculator. 37 divided by 41.23, it's going to be positive because a negative divided by a negative is a positive 0.8974. So to figure out what angle C is, I just have to do the cosine inverse of this. So cosine inverse on my calculator, cosine inverse of that answer, C is, in degrees, 26.18 degrees. That's the angle between those two sides. So the law of cosines is nice. When I know all 3 sides of a triangle, the law of cosines can help me find one of the angles inside of that triangle. Excellent. Did I do something wrong? Somebody said square root of 5. Square root of 5 is right here. And then when we squared it to get the 5, that's where that came from. All right. Well, thank you for that question. That one was a lot of fun. I've never done one like that, but it's a little bit of analytical geometry combined with a little bit of trigonometry. Really great. While we're talking about the law of cosines, a really neat thing to take a look at is the law of sines, because the law of sines has an interesting and often forgotten possibility that can happen. So let's take a look at the law of sines for your trig class. While we do, if you have any other questions that you want to see, maybe you're doing proofs in your class and you want to see more proofs, drop my calculator. If you want to see more proofs, stick it in the comments. If you want to see more solving equations, stick it in the comments. If you want tricks to how to solve the unit circle, how to memorize the unit circle, ask about the unit circle. Yeah, let's take a look, though, at the law of sines. The idea of the law of sines is if I know two sides and an angle, we can find the other angles, right? Let's find out. Let's say I've got a 5 over here and a 3 over here, and my theta, my angle theta is right here. That's what we're Actually, let's know that. Let's say we know that side. Let's say that angle is, let's do this angle actually. Let's say this angle is 28 degrees. The law of sines says that if you know an angle and the opposite side, those are going to make a proportion, a ratio, that's going to be the same regardless of which side and opposite angle. So let's find this angle here, theta, on this triangle. By the way, my drawing is not to scale, so we can't just rely on it being to scale. Let's see what happens when we take the sine of the angle, sine of 28, and stick it over the side across from it, 3, is equal to the sine of the unknown angle, that's what we're going to try and find, and put it over the side across from it, which is 5. Now it seems like to solve this, we should just multiply both sides by 5 to get 5 sine 28 over 3 equals the sine of theta. And I can figure out what that is using my calculator. 5 sine of 28 divided by 3. And the answer I get is 0.7825 after I round is equal to the sine of theta. Well, to get rid of the sine, we have to do the inverse sine. And so I'll do inverse sine of that number, and I end up with theta equal to 51.49 degrees. And if you put that down for your answer, your teacher is only going to give you a good maybe 3 out of 5 points on this law of sines problem because you have missed the most important part. Do you know what we missed? Stick it in the chat if you can see what we missed. I'll give you 3 seconds or so to figure out what was missed as we were solving for this missing angle. 2 seconds left. Get it in the chat. Do you know the answer? It's very subtle. It has to do with the unit circle. 51 degrees. Where's 51 degrees on the unit circle? It's probably around here. It's 51 degrees. Sine is the y coordinate. Oh, Blaze has it there. It just came in on my chat. Exactly. The sine can give us 2 possible triangles. There is a possible second answer. And so the idea is sine is the y coordinate, or how tall this point is. And if I go across the circle, there's another spot that has the exact same height as the spot my calculator found. My calculator is just going to find the first spot because it's a computer. It finds an answer and it's done. You have to be smarter than the calculator and know that there is a second spot that has the exact same height. And its angle is supplementary to the 51 because both of these are exactly 51 degree angles to come up to that same height. So if I want to figure out what this angle is, that possible angle, we're going to go the entire 180 degrees, and then we'll back up 51 degrees, or specifically 51.49. So I'm going to do 180 minus 51.49, and that's going to give me a second possible answer of 128.51 degrees. So with the information given on this triangle, we don't know. Remember, I mentioned this was not drawn to scale. Never assume anything in your trig class is drawn to scale because it's trying to trick you. This angle could be an obtuse angle with a side of 3 and 5 across from it, where the angle is 128 degrees, or this angle could be an acute angle where that angle is 51.49 degrees. And we have to account for both possibilities. All right, I see a great question coming in about graphing trig functions. We want to do a sinusoidal function, finding the amplitude and the period and whatnot. So let's take a look at that. Vaseline. I think is how you say that, from TikTok was asking about that. Remember, this is your office hour, so stick in the chat any questions that you're working on in your trig class. We are excited to help clarify any questions you have about trigonometry. And you're specifically asking about finding the amplitude and the period and whatnot. So let's go from a graph to an equation, and then maybe after that, we'll go from an equation to the graph. We can go both directions. So here's my axis. I'm going to stick the midline right here at, let's say that's 3 high. Go ahead and mark it. 1, 2, 3, 4, 5, 6. And then let's say we know that there is a point here at 1, 2, 2, 3 is a point on the graph. And let's go out 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, 1, 2. So we were at 2, 3. Let's go ahead and label that 2, 3. And this graph is going to start by going down, and it's going to wiggle, and it's going to come back. Let's go 1, 2, 3, 4, 5, 6 over, let's call that 6, 2. That's where it's going to wiggle back to at 8, 3. Which means it has to hit the bottom halfway in between there. 2, 8, 6, 4, 4, 5. We're going to put the bottom down here. Nope. Let's do this. I'm making it too hard on myself. Let's just keep it simple. Up. Middle. Can erase this point. Bottom. So here's my graph. And we're going to try and find the equation of this graph by identifying the amplitude, the period, and all those other pieces. So if we're starting from this point, the 2, 3, I see it is starting going down from the midline. Coming down from the midline is going to make it a sine curve. But remember, sine normally goes up from the midline. If you think about the unit circle, where the sine is the y-coordinate, it starts going up and getting bigger. We want to go down, getting smaller. So that's going to create a negative sine. So if we want to think about this equation, sometimes you see it written as a times sine of b times x minus h plus k. Well, A stands for the amplitude. That's how far the graph goes from the bottom to the top. Each one of those peaks and valleys. The valleys go the same distance. If you look at my graph here, that's going a distance of 2. So we're going to go negative 2 sine of B comes from the period. How long does it take before the graph starts to repeat? If I start here, the graph goes down, up, and back down. Right here, it starts to repeat. So the graph is going from there to there. It goes a distance of 1, 2, 3, 4. Period is 4. So we're going to take 2 pi and divide by the entire period of 4. That's what the B represents. 2 pi divided by the period. Then we have x minus h. H is the horizontal shift. How far have we shifted over horizontally to our starting point? That starting point is at an x-coordinate of 2. And then we're going to add to it k. K represents the vertical shift, specifically the vertical shift of the midline. So this midline is shifted up 1, 2, 3. And that gives us our function, our f of x, sinusoidal function, that is equal to this graph. And now I could use it to estimate other points. Let's say I want to know what it's doing here at 4 or at 2.5. You can plug those in for x and solve. Great question came in from TikTok, Italy, I think is the username. Question came in is, could it also be a cosine with a translation? Yes, that's a great question. The reason we picked sine is because we said we were going to start here at the 2, -3 point. But let's change things up and say, oh, I want to start up here at the top of the function instead. Starting at the top of the function, coming down is what the cosine graph does. So that function would be a cosine graph. It still has the same amplitude of 2. It still has the same period of 4, so we'll do 2 pi divided by 4. But what's different to account for the cosine, exactly like you said, a translation of pi over 2. Now, its translation, because of the period change, it's not pi over 2, but it's the same idea. Its translation coming over to this point is 1, 2, 3, 4, 5. So it's going to be x minus 5. And it still has a vertical shift of 3. Both of these graphs both of these functions create the exact same graph. And that's one of the cool things about trigonometry is sometimes there's multiple ways to express the same thing. So, for example, if I wanted to say this down here was my starting point, then it would have a horizontal shift of 3. We would subtract 3. But this starting at the bottom is a negative cosine. So we would do a negative cosine with a shift of 3. Everything else is the same. So every one of these has multiple answers that work. What's important is you pick a starting point so you know what you're going to use for your sine, cosine, positive, negative, and what your horizontal shift is going to be. All right. I've got somebody asking about the Pythagorean identity. It is one of the most used identities. Let's see, who asked that? It was from TikTok, and I don't know what your username is. I can't pronounce that. It's a couple symbols, but that's okay. We want to talk about the Pythagorean identity because this is your office hour, and I'm here to answer your questions. So do you have a question about your trigonometry class? Stick it in the chat, and we will take a look at it. And we are going to do a Pythagorean identity problem. Let me find one that looks fun to do. I am not seeing any on my paper. Well, I bet I have a solved one that uses it. So many papers. Proof. Solve. Here we go. Let's look at sine squared minus cosine squared equals 1 plus cosine squared. And let's just solve this on 0 to 2 pi for now. So we're not going to do all solutions. We're just going to see what the solutions are there. The idea of the Pythagorean identity is that we know that sine squared plus cosine squared is equal to 1. It's the most important Pythagorean identity. All the other Pythagorean identities come from this one. The idea is anytime I see a problem with sine squared or cosine squared, you should automatically think I'm going to use this Pythagorean identity because 99% of the time, that's going to be what happens. So from here, I look at the rest of the problem. Did I write it down right? I don't remember that cosine squared. Yeah, this last one shouldn't be squared. I'm sorry. The rest of the problem has a bunch of cosines in it. So let's try and match that by getting rid of the sine squared. So I need to know what sine squared is equal to. So we want to not have this cosine squared hanging out with it. We subtract cosine squared from both sides. And we see that sine squared is equal to 1 minus cosine squared. That means I can replace this sine squared with 1 minus cosine squared. And look what happens when we do that. We have 1 minus cosine squared of theta minus cosine squared of theta equals 1 plus cosine of theta. Whenever we have cosine squared hanging out with cosine, just like when we have x hanging out with x squared, we are going to solve it by setting it equal to 0 and factoring. Let's make the cosine squareds positive. So I'm going to add both of these. That's 2 cosine squareds, right? 2 cosine squareds added to both sides. That gives me 2 cosine squared of theta. I've got a positive cosine of theta. And if I subtract 1 from both sides, it's kind of nice. Those 1s go away. And I'm left with 0 equals 2 cosine squared plus cosine. When factoring, the first thing we always look for is a common factor. And sure enough, we have a common factor of cosine that we can pull out, leaving behind 2 cosine plus 1. When 2 factors are equal to 0, one of them has to be 0. So either the cosine of theta equals 0, or this factor equals 0. 2 cosine of theta plus 1 equals 0. Well, if I subtract 1 and divide by 2, we get the cosine alone. Cosine is negative 1/2. So we want to know when cosine is 0 or when cosine is negative 1/2. Goes back to our unit circle. Everything goes back to the unit circle, always and forever. Cosine is that the x or y coordinate? Think back. It's alphabetical. Cosine, sine, x, y. Cosine is the x coordinate. We want to know when the cosine is 0. When the x coordinate is 0, that happens at the top and bottom of the circle. That happens at pi over 2 and 3 pi over 2. Cosine is negative 1/2. That's just a little distance here. So the little distance gives us the top and the bottom. That's going to be 2 pi over 3 and 4 pi over 3. And so these become our 4 answers for this problem because I just said from 0 to 2 pi, so we can stop there. And that is our solution for cosine. Great comment came up as we were solving that, though. It came from TikTok from Gator Jr. 02. I'm not writing the opposite over hypotenuse stuff. That's a great way to keep track of and remember the different parts of the circle and where it comes from. Because you might remember the SOHCAHTOA thing. Some teachers still teach SOHCAHTOA. SOHCAHTOA. And that reminds us that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. The idea is in the unit circle, if I put an angle in this unit circle, there's an x-coordinate and a y-coordinate, and the hypotenuse of that circle, that is 1. So when we take the sine of the angle here, the sine of theta is the opposite over the hypotenuse. From the theta, the opposite is the y, and the hypotenuse is the 1. And that's what gives us that the sine is equal to the y-coordinate. So that's why I didn't write opposite over hypotenuse. I can just say sine is the y-coordinate. Same thing for cosine. Cosine is adjacent over hypotenuse. We'll go ahead and use capitals. Cosine is adjacent over hypotenuse. That's going to be the adjacent x over the hypotenuse of 1. That's why we say the cosine is the x-coordinate. So we don't have to write adjacent over hypotenuse. We can just say cosine is the x-coordinate on that circle. Excellent. I'm seeing a couple questions for, like I saw a question about, can I teach logs? I'll tell you what, with the logs, if you hang tight, we're going to do another live at 6:30 Pacific time, 9:30 Eastern time. That's going to specifically look at algebra, and I'll make sure logs is a topic in that. So make sure you log back into our live feed then, and we'll take a look at those. Let's take a look at sine over cosine and cosine over sine. Alejandro was asking about that. I think it's Alejandro Martinez. I see these mixed up all the time. Sine over cosine and cosine over sine. I wrote cosine twice. Cosine over sine. One of these is the tangent, and one of these is the cotangent, and we're going to look at a proof in just a minute where we use this relationship. And so we need to know which one is which. I like to remember, this is what works for me. Whatever works for you helps as well. If the co is on top, that's going to give us a cotangent. If it's not on top, that's going to give us a tangent. So tangent is sine over cosine. Cotangent is cosine over sine. A fun little aside that we don't really talk about much in trig, because tangent is the sine, how much is the sine over the cosine, and the sine comes from the change in y, and the cosine comes from the change in x. Tangent also becomes the slope of the line that you talked about in your algebra classes. So tangent and slope are the exact same thing. Kind of crazy. But I want to do a proof where we need to know tangent and cotangent, and here is a fun one. Let's say 1 plus tangent over 1 plus cotangent. We're going to show that that's equal to the secant divided by the cosecant. Now, with proofs, our strategy is going to be essentially the same. Strategy is going to be essentially the same is if you don't know what to do, change everything into a sine and a cosine. Sines and cosines we're a lot more comfortable with, and we can do some algebra with them. So tangent, we just put it on the board. Tangent is who over who? Do you remember? Stick in the chat. 3, 2, 1. Tangent is sine over cosine. Cotangent, remember it's got the co. So the co comes first. It is cosine divided by sine. We're also, with our proof, only going to work on one side. We have to work one side and show it looks like the other side. Whenever we do this trick where we change everything into sines and cosines, it's almost always going to create little fractions inside of a bigger fraction. And so how do we go about solving that, simplifying that? We're going to multiply by the common denominator. I see cosines and sines in the denominator, so we're going to multiply by cosine sine, and we'll multiply by cosine sine. It has to distribute onto both terms, so I might as well write it over here as well. Cosine sine, cosine sine. And the reason we do that is we're going to be able to reduce a cosine and reduce the sines. And so we end up with, let's see, cosine sine plus the sine times sine, which is sine squared, over cosine sine times 1 is cosine sine, plus cosine times cosine is cosine squared. We're going to want to simplify this fraction, and the way we can simplify this fraction, can't reduce. I always tell people, if you try and reduce when there's any adding and subtracting in the problem, a puppy dies. Don't kill puppies. But we can factor in order to solve. We're going to factor out the sign because factors can reduce. So when we factor out the sign, we get cosine plus sine over, factor out the cosine, and we get sine plus cosine, which is really nice because the sine plus cosine is the same on top and bottom, and it can reduce. Cosine's on the bottom. The reciprocal of cosine is secant. Sine is on the top. The reciprocal of sine is cosecant. And so we can simply take those. Sine is the reciprocal of cosecant. Cosine is the reciprocal of secant. And that's going to give us the original thing that we started with. We are just about over time, if not pushing going overtime. So I want to thank you all for logging in today. It has been such a much fun going over my love of trigonometry with you, answering your questions. I hope you come back next week. We are going to be here every Wednesday at 5 o'clock Pacific time, 8 o'clock Eastern time to answer your questions. And I know there's a lot of times to keep track of. So the easiest thing to do to stay updated is to scan that QR code up in the corner here to keep track of our live office hours. We've got live office hours for calculus. A lot of calculus questions came in. Come on Tuesday for those. We've got some algebra that we're going to do here at 6:30. Come back for that. Lots of exciting lives happening around chemistry, economics. Stay updated by clicking that QR code. Thank you for logging in. It has been so